Alrighty, we're back for another Ohio State Math OST standard review. Oh boy, it's been a long day. Today we're looking at standard 8.G.4. Let's hop right into it. Similar parallelograms EFGH and PQRS are shown. Now, it says what sequence of transformations can be performed on EFGH to prove that the parallelograms are similar. So when we talked about transformations, we talked about four kinds. We talked about reflections. We talked about translations. We talked about rotations. And we talked about dilations. And I said that reflections, translations, and rotations all produce congruent figures. Congruent meaning that it's the same side length, same angles, what have you. And dilations were the rare exception to the rule where it produced similar shapes. Where similar meaning that it's the same ratio of sides. So like you could double or triple it. But it doesn't give the same side lengths. So when I see that we're looking to prove that it's similar and not congruent, there's going to be a dilation somewhere. And you can tell it's a dilation because the new shape is noticeably bigger. So that's what a dilation does. It changes the size of the shape. So let's look at our choices here. A reflection across the x-axis and then a dilation by a scale factor of 3 centered at the origin. Okay, so let's look at one of our points. Let's look at point E. Point E originally would be 1, 2. Okay? If we were to reflect this across the x-axis, remember our rule for reflections, you negate the opposite letter. So if you reflect it over the x-axis, you negate the y. So 1, 2 becomes 1, -2. Then you dilate by a scale factor of 3. What does it mean to dilate by a scale factor of 3? That means you just multiply both numbers in your coordinate by 3. 1 times 3 is 3. -2 times 3 is -6. So now we go to 3, -6. And we say, is there a point there? Bam. There is. So now at this point, we have to make sure, is that the point that corresponds to E? So we talk about how order for letters matters. E is the first letter listed in the parallelogram, as is P. So P correlates to E. The fact that we got to P by doing this shows that it's A. If you weren't able to do that right off the bat, you could quickly eliminate B and D because a dilation by a number smaller than 1 means that the shape is getting smaller. And like I said, the shape is getting noticeably bigger. So it just becomes a question about whether or not it's a reflection across the x-axis or a 180 clockwise rotation, which is just essentially a double reflection. But we did A, and it worked out, so we go with A. The coordinate plane is shown. Ted draws triangle MNO in quadrant 3 of the coordinate plane. All right, let's draw a triangle MNO. Huzzah. He then applies 2 transformations to the triangle. First, the triangle is reflected across the x-axis. Okay, so our x-axis is right here. So we're going to reflect it, and it's going to look something like this. Like I said, it should look like a mirror image. The spots that are closest to the axes are still your spots closest to the axes. Your point here, that's the point farthest away from the axis, is still the point farthest away from the axis. Then, the triangle is dilated by a factor of 1/3 about point M. About point M prime, to create triangle PQR. Okay. So what this is going to do is it's going to take the first point, and this shape is going to shrink. Point M will stay where it is, but it's going to be a noticeably smaller triangle. I'm going to try drawing a different color to make it easier to see. I'm also going to zoom in a bit. Let's draw it in red. So it's going to be a noticeably smaller triangle, about a third of the size, in M, centered on point M. That's what it means when it says it's dilated by a factor of 1/3 about point M. Excuse me. So it says, which statement is true about PQR? PQR is congruent to triangle MNO. We know it's not congruent because we had a dilation. Dilation automatically makes it not congruent, which means B is wrong as well. Triangle PQR is similar to triangle MNO and is in quadrant 4. Quadrant 4 notably over here. Where is my shape? Notably not over there. It is in fact in quadrant 2. You would have been in quadrant 4 if you reflected over the y-axis, but we didn't. We reflected over the x-axis. So we ended up in quadrant 2, which is choice D. A horizontal line M is shown with two similar triangles, ABC and DEF. How can triangle ABC be transformed to result in triangle DEF? All right, so here's the thing. First thing you should notice, triangle DEF is bigger than triangle ABC. What does that mean? It means dilation. It means there's a dilation somewhere. Okay? We also note that triangle DEF is not overlaying or overlapping triangle ABC. That means it was probably moved via a translation. Because you notice the orientation hasn't changed. It hasn't flipped, so it's not a reflection. It hasn't turned. Like the shape isn't now like this, so it's not a rotation. It just moved. It stayed the same direction, right? Think of it like an arrow. If the arrow is still pointing down left, that's just a translation. If you rotated it, the arrow would probably be like this. If you reflected it, the arrow would be like this. But the fact that it's still like this means it is just a translation. So we're looking for dilation, translation. Check our choices. A reflection across a vertical line. No. A 90-degree rotation around point C. Interesting. No. A dilation, then a translation to the right. Bingo. Done. A dilation, then a reflection across a vertical line. If this was a dilation and then a reflection across a vertical line, I'm going to try my best to draw this, but we all know I'm not artistic. Your shape would look like that instead of being facing the same direction. So it is C. Parallelograms A, B, C, D, and W, X, Y, Z are shown. What transformation is used to show that the parallelograms are similar? A, using the word similar. B, it's notably a different size. It's dilation. This should take 2 seconds of thinking. If you see transformation, similar, dilation, and then you look, and like you didn't even have to look at the shape. As soon as you see similar, I want you to think dilation. But then when you look at the shape, you see that WXYZ is notably bigger than ABCD. Dilation. Two quadrilaterals are shown. Brian uses two transformations to show that quadrilateral JKLM is similar to quadrilateral WXYZ. What transformations did Brian use? So we see similar, and we see that the shape is noticeably bigger. So we're immediately going dilation. And we're eliminating any choice that does not have dilation. We eliminate choice D. So, this is where it gets tricky. This is where it gets particular. Okay? Because what this comes down to is order. Okay? So, I'm going to move where I wrote dilation here. And what this comes down to is order. Remember I talked about, I don't remember I talked about it in this video or only in the other videos, but the order of the letters matters. It's how the shapes correspond to each other. So I'm going to redraw the original shape as best I can. So quadrilateral A, or I'm sorry, JKLM, J is our first letter. W is our first letter in the other quadrilateral. So where J is here would be W in the free shape. K is the second letter. X is the second letter. So where K is here, I'm going to put X. L and Y correspond, and M and Z correspond. Now, here's what you have to look at, okay? If this were a translation, if you took this shape and you just moved it to the right, notice that the order of the letters didn't change. It would still be W in the top left, X in the top right, Y in the bottom right, Z in the bottom left. Does that happen in our shape over here? Does that happen in this shape? No. W is now in the top right. So, it's not translation. So now we're talking between rotation and reflection. So let's see if my... Will let me do this? Well, that's interesting. All right. So if you were to rotate, if you were to reflect this, like over a, let's say the y-axis, right? The spots that were closer to the y-axis, let's draw an imaginary y-axis right here. Okay, let's say this is the y-axis. The spots that are closest to the y-axis, which would be x and y, after you reflect the shape, would still be the spots closest to the y-axis. So it would be x and y. Your spots that are farthest from the y-axis would still be your spots farthest from the y-axis. Okay? Does this orientation match what we have? XY on the left, WZ on the right. Yes, it does. So this would be a reflection and a dilation. A rotation would end up with a shape, I want to say, actually I should be able to just get rid of this. I gotta get rid of all those, goodness gracious. Okay. A rotation should be easier for me to show off. So if you rotate this by 90 degrees, right, you see that W is now up here, X is down here, Y is over here, and Z is over here. Okay, so while W is where it's supposed to be and Y is where it's supposed to be, Z is not, and X is not. So that's why rotation doesn't work, and it has to be reflection. Two triangles are shown. What transformations can be used to show that LMN is similar to PQR? We see similar, we see different sizes, it's automatically dilation. All right, cool. I'm glad that we have established this because they've done it in so many questions. So let's get rid of anything without dilation. B and D, gone. Okay. So now it comes down to, is this a reflection or is this a rotation? And it all comes down to orientation. Okay. So L is at the very top. That should match with P. M is over here. That would match with Q. And N is over here. And that would match with R. Okay. Is there any way that you could picture a reflection where you end up with this orientation? I know this is easier for me to do because I have an iPad and I can actually just draw a shape and rotate it. But let's say that I have shape P, Q, and R. If I reflect it, I will just end up with Q still on the left, P at the top, and R all the way on the right. If I reflect it over a vertical line, if I reflect it over a horizontal line, I'll end up with a shape like this, which doesn't look like the shape we have. But now, let me take this and rotate it. Let's rotate it 90 degrees counterclockwise. And what do you know? It's the exact same shape. It's a rotation. All right. So that will wrap up this standard. I'll be back with more standards, but until then, thank you for watching. Good luck on your state test.